This is a demonstration of a file system implementation of the BBILLER Contract API. The Contract API is that interface between applications providing services to users and the BBILLER contract state machine and its storage of business documents and the states of a business process. In this demonstration, the implementation is in a file system and not in an actual blockchain. The Contract API is fully implemented in this demonstration, and it provides the interface between a Python service that provides services to a user on the command line. The Contract API encrypts and stores the business document in a different location, and the states are preserved in the file system in order so they can be reviewed as if they were blocks in the blockchain. The state machine used in this demonstration is a simple state machine for invoicing. In this simple invoice process, there are 2 or 3 participants, at least a supplier and a customer, and perhaps an authority. The state machine has 2 starting states, clearance model or direct model, and 3 ending states, voided, paid, or unauthorized. Which of the first 2 starting states is used depends on the presence or absence of an authority party in the transaction. When the transaction is initiated with an authority party, the clearance model is engaged and the initial state sits with the authority to make the choice regarding whether to issue the invoice or to mark it as unauthorized. In the absence of the authority, the initial state is the direct model, in which case the customer has the current state of issued, and the customer decides whether to dispute or accept the invoice. Should the customer dispute it, the status is then handed back to the supplier, who decides whether to issue the invoice or to void the invoice. Setting the state to issued again does not change the invoice. It merely states that the dispute is not agreed to and that the original invoice is to stand as issued. The customer then can decide to accept the invoice. They could dispute it again, but should they decide to accept the invoice, then at the point where they make their payment, they change the state of the document to remitted, and then it is up to the supplier to decide if enough money was remitted. Should there not be enough money remitted, they can change the state to underpaid, in which case it's back in the hands of the customer to decide to remit more payment. When they've done so, they indicate the payment as remitted, and then the user can decide that in fact the invoice has been paid. So this is the state machine that the process will follow once the contract is initiated, and the state machine is supplied as one of the arguments of initiation. In this first scenario, the first step that we're going to take is to actually make the keys for only the supplier and the customer. Given that the authority is not present, that means that the direct model is being used, and so when the supplier initiates the state machine, the state will be set to issued, and it will be in the hands of the customer to then make the decision of what to do. We'll make the document, and then we will make the contract, which initializes the state to issued, and then we'll have the customer accept the document. We'll expose some information that was added by the customer. We'll change the state to remitted, and we'll again decrypt some new information that replaces the old private information. We'll change the state by the supplier to underpaid. Apparently not enough money was paid. The customer then changes the state to remitted after having finished the payment, and then the supplier will determine that enough money has been paid and the process is done. So let's run our first scenario. Here we have made the keys for both the customer and the supplier. If we look at the difference between a public key and a private key for the customer, the public key is the information that is sent out to the general public in order to access information that has been encrypted or authorized by the customer. The customer has a private key that they use to authorize actions and to encrypt information. In the next step, we make the document. In this case, our document is a simple text file. The BBILLER Smart Contract is agnostic to the format of the business document. It could be a PDF file, it could be a text file, it could be an XML file. Next, we start the contract. Our scenario for the contract is in this file, scenario load, and we can see that the scenario includes a definition of the state machine, the process definition, with its initial states based on the presence or absence of the authority, and the different state changes that are described by the diagram showed earlier. In our list of roles for the state machine, we can see only the supplier and customer. There is no authority listed here. And there is some public information and some private information that is to be made private in the smart contract and accessible only to these parties. This contract is making a reference to another contract. If we look at the resulting contract, we can see a date and timestamp, a digest, a SHA-256 hash of our input document, a URI of where the encrypted document is being stored. We can see over here, if we expose the first, say, 39 bytes of the document, we can see it exposed here. And we can see that our process definition has been moved from the scenario into the contract. The indentation of the information in this JSON file is different than the indentation that was used in the authored JSON file for the scenario, but otherwise the content is identical. We can see private information that has been encrypted. So our private annotation down here, this JSON structure has been encrypted for use later by any of the parties. The process definition has been transcribed from the scenario definition into the smart contract. We can see the indentation is different, but that's just the way the JSON files are being presented. The public information, the public annotation here, is preserved and it is visible to the general public, anyone who looks at the contract. The roles of the players involved have been transcribed. The key information has been encrypted so that the general public cannot see the keys that are used for all of the encrypted information, but in this case, the supplier can use his private key in order to decrypt this information and have access to the key that is used for all of the other encrypted information. Each of the roles might have private or public information. The private information is visible only to the other roles. The public information is available to everyone. The public key is available to everyone should the role decide to encrypt information later on in the process. And the state has been set to issued, and one step of the state has been accomplished. Next in our demo, we have the customer changing the state to be accepted. We now have a history of the contract in what would be blocks in a blockchain, and in this mock-up are files in the file system. If I compare the old step 1, if we go to the bottom, we can see that our old state is the issued state and the new state is the accepted state. Going to the top, we can see that the timestamp has changed. None of the other information has changed except under the roles where some bill has been used to pay off on the activity of the contract. The initial state of refunded has been changed by the customer to be shared. No other information is changed for the roles, and as I showed earlier, the state has changed to accepted. We can see, using the decryption task, using the document key, that the private annotation JSON encrypted, when it is decrypted, is a JSON structure, as we saw in our initial scenario load. Next in the demo, the customer is changing the state to remitted because they have made a payment and they're claiming that the payment has been fully remitted. If we take a comparison now of the state 2, which was accepted, is now step 3, with the state remitted. At the time, there's a new private value and a new public value for the annotation, and we can see that indeed the annotation has changed. And if we go up to the private annotation that's encrypted, it too has changed. And it's still not visible to the general public because the public does not have the document shared key. Any one of the parties, however, can go to the encrypted key here using their private key to obtain the document key, which has access both to the business document and to the private annotation. We can see now when we decrypt the same field, the private annotation JSON, the one up here with the new data, we get the new private value, and the old JSON structure has been replaced. Next, the supplier has determined that not enough money has been paid, and so they changed the state to be underpaid. We can see the state change from remitted to underpaid in step 4, which is after step 3. Next, we have the customer changing the state to remitted because they've made a supplemental payment. The state changes from underpaid to remitted in step 5. And in this case, the supplier has determined that it is enough money. So the supplier changes the state to paid. The state goes from remitted to paid, step 6, and we are now at the end of the state machine, and so there's nothing more to be done with this smart contract. All of the money has been refunded, there is no balance for any of the parties, and the history of the entire transaction, all of its steps, the last step, are all stored on the blockchain, or in this case the file system, as a distributed business transaction repository. The last steps in the demonstration expose the information to the runner of the scenario just for information purposes. All scenarios are using the same state machine for a simple business process for an invoice. In scenario 2, I'll show how the same state machine is impacted in the presence of a third party, the authority. With the authority present, the initial state of the state machine becomes the clearance model. In scenario 1, in the absence of the authority, the initial state of the state machine was the direct model. So to accomplish this, we'll make the keys for the three parties, the supplier, the customer, and the authority. We'll make the same document, but this time we're going to try to make the contract with the credentials of the incorrect party. We will then make the contract with the proper credentials of the supplier, and that will initialize the state to reported because there is an authority party defined for this scenario. We'll then try to change the state from reported to issued, but by using the supplier credentials, this will fail. Only with the authority credentials can we change the state of the machine to be issued. We're then going to try and change the state machine to accepted, which looks like it should be allowed, but the customer has to use, as well as his credentials, the appropriate state of the state machine. This prevents a situation where some party might inject themselves into the process without the customer knowing. The customer has to make a state change at an agreed upon step. Then we'll have the customer properly accept the document at the correct step. I'll expose some of the private information. The customer will report a remittance. The supplier will indicate that it's underpaid. The customer will then support a remittance again, and the supplier will indicate that indeed it is fully paid, just as in the last scenario. But what this scenario shows is both the different behavior in the presence of the authority and some examples of failure conditions when making calls to the BBILLER smart contract. So in our new scenario, for scenario 2, we see there are now 3 parties, 3 roles that are involved: the supplier, the customer, and the authority. And using the same process definition, the same state machine as in the earlier scenario, we see that in the presence of an authority, the initial state of the state machine is reported and not issued. So first we make the keys for the 3 parties: the authority, the customer, and the supplier. Next we make the document itself. It's the same document as before, a simple text file. Here we've tried to initiate the contract, but we've tried to use the customer credentials to initiate the contract. As I showed in the state machine diagram, only the supplier can initiate the contract. Accordingly, we get a failure indication, unauthorized request. The customer is not authorized to load a new scenario. So here we are using the supplier credentials, and the report is successful. The load of the document has encrypted the document, and you can see from the first 39 bytes shown here that it is unintelligible. We do not see the content of the invoice that I've shown up here. We do not see that in the encrypted document inside the smart contract. And if I expose the current block, the block has been initialized at a given date and time. The process definition here has been transcribed into the smart contract. The roles have been transcribed into the contract while encrypting the key information using the public key, so that each of the roles can use their private key in order to pull out the document key information. The private information that was in the scenario has been encrypted using that document key, and it is available to all of the parties. So this is private information that is private to all within the transaction and not to anyone outside of the transaction. This is not meant to be private information only to the supplier. This is private information about the transaction that is visible to the other parties because it has been encrypted using the document key that was used to encrypt the business document itself. Next, we've tried to change the state to issued, but the supplier is not authorized to change the state to issued. The state machine is initialized in the clearance model, and as such, only the authority can change the state of the state machine to be issued. Accordingly, we get a failure here. The reported state, which is the current state, and we see that down here in our block, our blockchain block, which in this Python implementation is a file. We see here the initial state is reported, and the reported state does not involve the role supplier. It only involves the role authority. And here we have successfully changed the state to issued using the authority credentials, And if we compare the old initial contract to the new state of the contract, we see a change in the timestamp of the operation. We see bill having been deducted for the cost of the transaction, and we see that in step 2, the state of the state machine is now issued. Both blocks would exist on the blockchain as they exist here in the file system as separate files. In this test of a failure, I am using the customer credentials to indicate that the invoice is being accepted, which is correct. The customer does have the privileges to do that, but the customer is asking to do this at step 1 of the process. And we can see here that the current step of the process is 2. And so the failure message reads, transaction expecting step 2, but step 1 has been requested by the customer. This is a fail-safe mechanism to ensure that the customer is accepting the state machine at the step that they know and not at some new step that someone else might have slipped in. And so all requests by any participant in the process has to be accompanied by their expected step number when they make the request. That way, they are not making the request on a change to the state machine that they might be unfamiliar with. So here I've revised the request to change the state to accepted, indicating that I am modifying step 2 of the process, and it is indeed step 2, and so the contract changes. Now comparing the state of the contract, it has now gone from step 2 to step 3, from the state of issued to the state of accepted. Here I'm exposing the private information. The information is here shown to be encrypted, and when I decrypt it, I get a JSON structure of private sample with a private value, which was in the original scenario definition. I now change the state to remitted, and in that process, I am changing the private information and the public information. I am making this request on step number 3, and we see here that the current step was 3. It has been successful, so I can now pull down the old step 3 and compare it to the new step, and we see step 4 is remitted, and the information up here, the private annotation, has changed. It's still encrypted. We still need the document key to expose it, which we will in a moment, but the private information has changed and the public information has changed. In this case, from a JSON structure to a simple string. So now we expose the information here, this newly encrypted information, with our key, and we see the string value instead of what I showed earlier as the JSON structure. Step 4 is being changed to step 5 by the supplier, indicating that the remittance was insufficient. We can see here step 4 to step 5. The remittance is now underpaid. The customer remits more. The state changes to be remitted. This satisfies the supplier, so he changes the state to paid. And the process is complete. Paid is one of the end states of the state machine. Since the process has finished, the bill balance has been refunded. It was 35, 2 were used in the running of the smart contract, and so 33 is being refunded to the supplier at the wallet address of the supplier, which we can see to be here. The demo continues to expose the private information and to expose the actual document key that is used to get access to the private information. Each of the parties uses their private key to access the document key from this encrypted string here. The smart contract has used each of the participants' public key to encrypt that key information, which means only the participant can decrypt their field in order to get the document key for their use in the other private information found in the contract and in the business document itself, in this case, the invoice. In scenario 3, I'm again going to involve all three parties. We're going to make the document, we're going to go through the initial parts of the process, but at this point, all of the parties determine that there is no need to continue. For some business reason, we need to now terminate the smart contract, refund all of the unused bill that was put into the smart contract to pay for the transactions, and terminate the contract so that it can no longer be used. I try various combinations that will either return a failure or not change at all because the conditions are not fully satisfied. First, let's look at the scenario definition that I'm going to load. We see the same definition of the simple invoice process, and we see the involvement of three different parties. This will engage the clearance model of the simple invoice state machine. We first make the keys for the three parties. We make the document. And we load up the contract. We can see the state machine has been transcribed. We see the three roles having been loaded up, and all the appropriate cryptographic transformations have been accomplished. Here, the authority has authorized the invoice, and so it becomes issued. We see the timestamp has changed, and the state has changed from reported to issued, and we are at step number 2. Here the customer is changing the state to accepted from step number 2, and that's correct. So if we check step 2 from the current step, we see the state has changed to be accepted. Now here we're asking to terminate the contract. All three parties have agreed that the contract needs to be terminated for some reason, and in this case the presumption is the contract is at state 2 when the credentials for all three parties are given in order to terminate the contract. But we can see that the contract is at step 3, not at step 2, and so we get the appropriate failure message that the transaction is expecting step 3, but step 2 was requested. At the same time, the termination request is trying to add new private and public information to the contract. Perhaps it's an explanation of why the contract was terminated. But decrypting the information, we see that nothing has changed. The private information was not changed. The public information here was not changed. because the request to terminate the contract failed with the incorrect step number. Here we are trying to terminate the contract, but we don't have enough credentials. We are asking the contract to be terminated with the credentials of the customer and the authority, but we are missing the credentials of the supplier. And so we get an authorization failure indicating you don't have enough authorization to terminate the contract. Again, there's no change to the encrypted information. Here, we are trying to pass the customer credentials twice and the authority once, so we're still missing the supplier credentials, and so we again get a failure of unauthorized request. Again, no change to the private information. And finally, we supply the customer, the supplier, the authority credentials at the correct step number, supplying new private and public information. Everything is aligned, and we look at the difference between step 3 and the final contract. Step 3 to step 4, the state from accepted to empty state. So this is terminated. It's not one of the defined end states. It's a generic termination end state that is telling the readers of the blocks that all of the parties that were party to this transaction agreed to terminate this contract at step 3 using their private key credentials. And so that has authorized them all to terminate the contract and refund all of the unused bill payment. We see here that each of the parties happen to have some bill accumulated in their balances, and they have all been refunded. We now see that the private information has indeed been changed. It's still only accessible to the parties with the document key that can be accessed using their private keys, but the information has been changed and remains invisible to the public. The public information here has changed from the old JSON structure to a simple string, as was indicated on the command line. We have access to the private information of, in this case, role 0, which is the first role, the supplier role. And we have access to the symmetric document key. In scenario 4, I demonstrate how one might implement factoring an invoice. And this involves changing the ownership of the invoice, or changing the supplier to whom the money for the invoice is owed. We are going to make the keys for the supplier, the customer, and the authority. We're going to make the document. We will initialize the contract. We will then have the authority change the state to issued. The customer will change the state to accepted. We're then going to show how we can add more bill for the supplier. And then we're going to show how we can add bill for any one of the parties, in this case the supplier. But at this point, the supplier decides he's going to sell off his invoice to a factorer. And so we need to change all of the private key information and the role information from the supplier to the factorer. And so when the customer comes to make their payment, they can see who in the smart contract owns the invoice, and therefore to whom the money is owed. We'll then decrypt the private information that the factorer has added to the contract. Perhaps it's his account information. We will add new bill for the factorer, who is the new supplier, because when we replace the role of the supplier to the factorer, all of the supplier's bill gets refunded. The factorer becomes responsible for the costs of running the state machine. The customer will then indicate the payment has been remitted, and now the factorer will change the state to paid. The supplier's credentials won't work at this point, and then we'll show the private information. So let's look at the scenario load information. We have the same state machine. We have, again, 3 parties. Again, there is a reference to some other BBILLER smart contract that reflects perhaps an order that this invoice is responding to. And we run our scenario. This time we're going to make keys for the supplier customer authority and our future factorer. This factorer is not involved at the beginning of the process, but we'll need these keys later on in the process. We make the document. We initiate the contract. Step 1 is reported by the supplier, ready for the authority. The authority changes it to issued. Step 1 to step 2, from reported to issued. We see on the blockchain, or in this case the file system, the original step 1 block, and now the current block at step 2. Here the customer has changed the state to accepted. In step 3 from step 2. Here the supplier has topped up by 10 their bill for use in the future. If we look at the bill, it has gone up from 41 to 50. 10 was added, but 1 was taken away for the cost of doing the transaction, and so the balance is 50. At this point, the supplier sells off the invoice to a factorer. The factorer now owns the invoice, and so the information for the supplier has to be changed from this party to be the factorer party. And this is done with the credentials of both the supplier and the factorer, the supplier saying that at step 4 of the contract, please change my role information to be the factorer's role information as encoded by the factorer. We see he is taking over the supplier role with the factorer credentials. The act of doing so has refunded the unused bill to the supplier. And we can see here that the contract has changed state. We have gone from step 4 to step 5. The state change hasn't changed, but the state of the contract, because the role of the supplier has changed. We have new wallet information, we have new encrypted key information, we have new private information, all coming from the factorer, who is now in the role of the supplier. We can see here the private change and the public change. The public change gets reflected publicly, and the private change is encrypted. We can decrypt it using the document key information. And now we have the factorer adding bill to the contract for his use. And we can see that from step 5 to step 6, the amount of bill has gone from 0 to 19, because 20 was added, but 1 was used in order to effect the transaction. Here the customer is indicating they've remitted payment. It's gone from 6 to 7. And here the factor has agreed the payment has been made. And so we compare the old state 7 to the new current state as paid. The unused bill has been refunded to the supplier role, in this case the factorer. And there has been new private and new public information added at this point, and so we can see it's changed here in the private and changed here in the public. And so the state has reached the end, and we can expose the information as we have before. This final scenario explores the adding and the using of bill to the smart contract in order to pay for the transactions being executed. As before, we'll make the keys for the parties involved, we'll make the document, and we'll initialize the contract to the state reported using a set amount of bill by the supplier. We'll then change the state to be issued by the authority, and the authority is going to not only pay for the transaction, but contribute a bit extra in order to illustrate components of this demonstration. The customer will change the state, it'll dispute the invoice, the supplier will say, no, you're wrong, it's okay, and this customer will say, well, no, I really want to dispute it, and the supplier will again say, no, it's okay. Now, by the time we get to this point, we'll see some of the usage of bill and how it is distributed across the different parties. We'll then try to change the state by the customer, but it will fail because there's not enough bill in the contract to do it. The customer will then pay for that and pay for remitted. The supplier will then try to mark it paid, but it too will fail because there's not enough bill, and then the supplier will have enough bill to pay. In the loading of scenario 5, we see that the initial balance for the first party, the supplier, the initial balance is 15 bill that's going to pay for the running of the contract. Let's now run the contract. Here we've created the keys as before. We've made the document. And we've used the JSON of the scenario to load up the contract. The initial state of the contract we see is reported because, again, we have the authority as one of the parties, and the initial state for the state machine, when the role of authority is available, is reported. The supplier has used 15 bill to initialize the contract, but there's only a balance of 10 because 5 have been used in the load process. It should be noted for this demonstration that the choices for the amounts of bill being consumed are arbitrary at this point in the development. Here the authority has changed the state to issued. We can see the state having been changed from reported to issued, from step 1 to step 2. The authority used 6 bill when invoking the call. Only 3 bill were used, and so there's a remaining balance of 3, and the authority has indicated that the overpayment is to be shared amongst other users. In the real world, I wouldn't anticipate an authority to be doing this, but setting it up this way in this demonstration helps us talk more about the way that bill is expended. Here, the customer has changed the state to disputed. And 3 bill have been taken off the shared balance of the first balance that's available. The customer has no balance available, but the supplier has indicated the overpayment is to be shared amongst the other parties. 3 bill then are taken off in order to pay for the state change from issued to disputed. In the scenario, the supplier does not accept the dispute and so changes the state back to issued. This has cost 3 more bills, so we see the bill balance reduced from 7 to 4, and the state changed from disputed back to issued. Nevertheless, the customer wants to dispute the invoice once again. The state changes from issued to disputed, the balance is dropped from 4 to 1, and the step moves from 4 to 5. Of course, the supplier hasn't changed their mind, and so it is still issued in their mind, and so they change the state to issued. The cost of the change of the state is 3 bill. 1 was taken away from the balance for the supplier. The supplier was the one engaging the state change. 2 still need to be found. And the contract looks down the list of roles, finding the next role that has a shared overpayment status, finds that there are 3 bill available in the authority balance, and uses the remaining 2, dropping the balance to 1, in order to change the state from disputed to issued. Here, the customer is now trying to say accepted. However, the error is reported insufficient bill to pay for the transaction. This is because there is only 1 bill available in all of the balances. The customer is not contributing any bill to the task, and so the state does not change and the transaction does not happen. And so the customer tries again, this time supplying 3 bill in order to pay for the transaction, and the transaction is successful. All 3 of the bill were consumed, and so there's no balance, and if there had been a balance, it would have been refunded, because that's the state of the overpayment for the customer. The state has changed from issued to accepted, step 6 to step 7. The customer then changes the state to remitted, supplying 3 bill to do so, and we have a new state of remitted. For step 8, the 3 bill that was supplied were all consumed. We still have a balance of 1 left for the authority. Here, the supplier has tried to change the state to paid. They haven't supplied any bill, and there is insufficient bill balance in the contract, and so there is a failure. The supplier then supplies the 3 bill that is required. The state changes from remitted to paid, that is step 8 to step 9, and the balance that was the 1 for the authority has been refunded. And so what we have seen in this demonstration is that I have used the command line to invoke services written in Python that go through the BBILLER Contract API to a file system implementation of the BBILLER state machine written in Python. The business document supplied to the Contract API has been encrypted and stored in its own location, and each of the state changes has been stored as a separate file in the file system. This mimics the separate states in a blockchain. When a service provider is addressing services for the users, they invoke the Contract API in order to store the business document, the initial state, and all of the state changes as triggered by the users. In the same way that any of these states can be inspected after the fact, the same way that the file system files can be inspected after the fact, implements a distributed business transaction repository. And when each of these smart contracts is linked to other smart contracts in the fulfillment of an entire business process between different parties involved, you have a complete distributed business transaction repository of the entire interaction between all of the parties. This has been a demonstration of a file system implementation of the BBILLER Contract API. For more information on the blockchain implementation of BBILLER, please see bbiller.com.